In today's session, I'll be discussing on a problem which is called as traveling salesperson problem, which can be solved by using dynamic programming approach. So let us first define the problem statement. Given a set of cities and given distance between every pair of cities, the problem is to find the shortest possible route where every city is visited exactly once and finally return to the starting point. This is how the traveling salesperson problem is defined. Within the problem, a set of cities will be given. Between every pair of cities, distance will be specified and given a starting point, a starting city. The problem is to find the shortest possible route to visit every city exactly once and return to the starting point. So wherever we have started from the starting city, start from the starting city, take the shortest route, visit every city exactly once and return back to the starting city. You'll have to find such a shortest route from the given set of cities. So the same problem when you have studied in your discrete mathematical structures course, you might have studied the problem as given a graph. You might be asked to find a minimum weight Hamiltonian cycle. It's the same approach. It's the same problem, and finding the shortest route among the cities, it's the same as finding minimum weight Hamiltonian cycle. Now, there are two solutions, or maybe more number of solutions that are possible. For now, I'm going to compare the brute force approach with the dynamic programming approach. A brute force approach is the technique where you are going to find out all the possible routes. Find out all the possible routes. And among all the possible routes, find the optimal route. Find the optimal route. And the optimal route is the one with the shortest distance. And if you are using brute force approach, a blind approach, attacking the problem without any particular technique, then it is going to take n factorial amount of time. If there are n number of cities, it is going to take n factorial number of possibilities. That is, given n number of cities, there will be n factorial different possible routes. And all the n factorial different possible routes, you'll have to explore, find out the distance for each route so that you can select the best route. And you may assume that the time complexity will be n factorial. So this n factorial value will be large, very, very large. So hence we'll not attack this problem by using brute force approach, but rather we'll solve the problem by using some technique wherein the number of routes that you have to find out, those will be reduced. That will not be n factorial, but the number of routes that you have to explore will be reduced. And for that, here we are talking about dynamic programming, using which we are going to solve traveling salesperson problem. And using dynamic programming is nothing but you are attacking the problem, you are solving the problem by using some logic, some technique. So that's why the solution can be obtained in lesser time than n factorial. So the problem will be represented like this. You may say that a set of cities are given, Between every two cities, distance is specified. You have to find the shortest route. Everything will be there. But because we are computer science people, whatever problem has been given to us, we have to first represent it, through which further it is easy for us to compute. Right? So for that, for the given set of cities and the distances, we are going to represent this information, the cities and distances information, by using a graph. And that too, this graph will be a directed graph and weighted graph. It will be a weighted directed graph. That is, this graph G will have a set of vertices and a set of edges V, E. V is the set of cities and E is the set of routes between every two cities. So this is how we are going to represent the information. Each city is represented as a vertex in the graph. The route between every two cities will be represented in the form of a weighted edge. And if you have some cities, two cities, ith and jth city, then there will be an edge connecting ith city with the jth city. That is, between ith city and jth city, there is an edge that is connecting them. Then if there is a direct route between I and j, then naturally there will be a weight associated with this edge. And the weight is nothing but the distance between the ith city and the jth city, which is represented as Cij, where C is the cost. Cij is the cost between ith city and jth city. There is also other possibility that there is no direct route between I and j. There is no direct edge connecting I with j. Then in such scenario, the distance between I and j will be initially taken as infinity. Later, it will be modified depending upon how you are going to find the roots. But initially, this will be the default values. If there is a direct edge between I and j, then that will be the C of ij. If there is no direct edge connecting I and j, then the cost function Cij, you'll start by taking it as infinity. And here, the assumption is that all the weights or all the distances between the cities should be non-negative. That is, distance can never be less than 0. Distance can never be negative. Distance may be 0. That is, if you take distance from the city to itself, then the distance will be 0. If you are taking distance from one city to another city, distance may be 1 or more, but distance can never be less than 0. So here, this traveling salesman problem is assuming that all the distances are non-negative. So we'll check up some formulae because we are talking about dynamic programming approach for solving the problem. So we'll find out this formulae and how it works. So for simplicity, it is being assumed that the starting city is vertex number 1, but it is not so. Maybe, for example, if I have some graph like this, where there are 4 cities. So the 4 cities are represented by using 4 vertices, and there will be directed edges which will be connecting any 2 cities, and these edges will be weighted. So the distance will be the weight of the edges. So the weight may be something like this. So this is how you are going to represent the information of the traveling salesman problem using a graph, a directed weighted graph. Each city is represented as a vertex, and directed edges represent the distance between the two cities, between any two cities. Now, for simplicity here, I am assuming that the starting city is vertex number 1. It is not mandatory that the starting city should be vertex number 1. It may be vertex number 2 or 3 or 4. Now, if I consider the starting city as 1, then the challenge is that you have to find shortest route to traverse through the remaining cities. What are the remaining cities? The remaining cities are 2, 3, and 4. Now you have to start from city number 1. Then you have to find shortest route through which you can travel to city number 2, 3, and 4. And then finally you come back to the starting city and stop. You start from city number 1. Then you have to find shortest route through which all the remaining cities can be traveled. So you have to find shortest path from 1 to the remaining 3 cities. And then finally you have to return to the starting city number 1. So this path may be 1, 2, 3, 4, and 1. This might be the shortest path. And the order of travel, you can see that 1, 2, 3, 4, 1. That is the order in which the cities will be traveled. You'll start with city number 1, then you'll go to city number 2, then to city number 3, city number 4, and come back and stop at city number 1. This might be the shortest path, or this might be the shortest path. 1, 3, 2, 4, 1 might be the shortest path, or 1, 4, 2, 3, 1 might be the shortest path. So there might be different routes through which travel can happen. But among all these possible routes, you have to apply dynamic programming approach, and you have to find the shortest route that is possible. That is, you have to find an optimal route. And the dynamic programming supports with finding out the shortest route, first thing. Then the second thing, there might be many possible routes. All of them you have to check out. All the possibilities you'll have to verify. Then you have to select the optimal route. Now there might be many possible routes, all of which if you want to check out, it may take large amount of time. Now dynamic programming, it also supports some rules, some restrictions while going through these routes, that you don't have to explore all the possible routes. If you don't have to explore, if you don't have to verify all the possible routes, then the time complexity also will get reduced. This is how your dynamic programming approach is going to support traveling salesman problem. So here, let us check out what is the formula here. So the traveling salesperson problem is to determine shortest path that starts and ends at vertex number 1, assuming that vertex number 1 is the starting city, which is represented as a function g, where g is the cost function, which will have 2 parameters. It's a function which takes input 2 values. What is the starting city? The starting city is 1. Then, what are all the remaining vertices or the remaining cities through which the path has to be found? What is the starting city, comma, what are all the remaining vertices through which the shortest route has to be found? So here I have written this as 1, comma, that is 1 is the starting vertex, comma, Why I have written v minus 1? So this v minus 1, so if you take v, say for example, v is the set of vertices which might be, as I have taken in the example, there are 4 vertices representing 4 cities, 1, 2, 3 and 4. Now, among these 4 vertices, this first vertex is the starting city. What are all the remaining vertices through which you have to travel? And for traveling, you have to find the shortest path. The remaining cities will be 2, 3, and 4. How can you write 2, 3, 4? You can write 2, 3, 4 as the subset of V. And that subset of V can be mentioned as V minus first city. Total number of vertices V minus the first city, that will be the subset of V, which is 2, 3, 4. That is what I am indicating here. G is the cost function. That is the cost of the route, where the starting city is first city and the remaining nodes or the remaining cities will be 2, 3, 4. And this function, cost function G, is going to give you the length of the shortest path, starting at vertex number 1 and going through all the remaining vertices V minus 1 and again terminating at vertex number 1. Right? So this G is the cost function. Now further, if you see this formula, how can this G1 comma V minus 1 can be calculated? So here G1 is the starting city, V minus 1 is nothing but 2 comma 3 comma 4. How can now I calculate this? This can be calculated as C1k plus G of k with V minus 1k. So this is nothing but a recursive formula. A recursive formula which will be called repeatedly again and again on the remaining nodes. So initially I'll start taking city number 1 and the remaining nodes will be 2, 3, 4. Then what will actually happen here is I'm going to find out what is the distance between city number 1 and city number 2, which is C of 1, 2. C of 1, 2 is the distance between city 1 and 2. That is given a graph something like this, where there is a direct node with the distance C1, 2. Now, there might be also other cities like this. So now what is going to happen? I am starting at city number 1 and the remaining nodes are 2, 3, 4. The remaining cities are 2, 3, 4. Now I have to select among the remaining nodes which will be the next city after 1, which is the next city that I am going to travel to. The next city I am going to travel to may be city number 2. I can go to city number 2. I can go to city number 3, or I can go to city number 4. There are 3 possibilities. Maybe I have selected that from city number 1, I'll travel to city number 2. Then the formula goes like this. So from city 1, you have traveled to city number 2. So that is C12 plus G of, now your starting city will be 2 because right now you are at city number 2. So now again you have to find out the cost function, but the parameters are going to change. Now the starting city is 2 and the remaining nodes, the remaining cities to which you want to find the shortest route are 3, 4. In this way, the formula is a recursive formula. the process itself is a recursive process. You'll start at some city, starting city. You'll have the remaining cities. Then among the remaining cities, you'll select any one city to which you'll travel next. And whichever city you select, that will become the starting city. And further, there will be remaining cities and so on. So this will continue like this. And finally, at some point of time, you are going to reach a city I. This is ith city, after which you have nowhere to travel. You have started from 1, you went to 2, 3, 4, for example. I am right now at 4th city. From 4, I don't have anywhere to travel. City 2 is already visited, city 3 is already visited. Now I have visited city 4. Now I don't have to go anywhere. So what I'll do, wherever I have started, I'm going to reach back to the starting city. So that is represented by a cost function, which is g of I, 5. I have reached some ith city from where I have to return to the starting city. And the cost function here, g of I, null, will be equal to the cost of traveling from ith city to the first city. From traveling from ith city to the first city, right? So this will be the formula that you are going to use. So further, we'll try to solve a problem.